If the universe is so unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, then where is everybody? This simple yet haunting question lies at the heart of the Fermi Paradox, one of the most profound mysteries in our search for extraterrestrial life. Statistically, the cosmos should be teeming with civilizations, their signals buzzing across the void, their ships drifting between the stars, and yet, when we listen, when we look, silence. An eerie, almost unsettling emptiness stretches beyond our pale blue dot. Why? What if we're not just searching for aliens, but for an answer to something far bigger, a clue about the fate of intelligence itself? Think about it, our galaxy alone is over 13 billion years old. Plenty of time for countless civilizations to rise, expand, and leave their mark. So why does it feel like we're standing alone in a cosmic desert? The implications are staggering. Maybe we're the first, maybe we're the last, or maybe the universe hides dangers we haven't even begun to imagine, forces powerful enough to silence entire civilizations before they ever get the chance to reach out. This isn't just science fiction. The Fermi Paradox forces us to confront realities that could reshape our future, from the technologies we develop to the way we see our place in the cosmos. So let's embark on a journey, one that takes us from the crowded streets of Earth to the silent depths of space, searching for answers to humanity's greatest question: are we truly alone? Along the way, we'll explore the most compelling theories, from hidden alien superstructures to the terrifying possibility that advanced civilizations inevitably self-destruct. We'll examine how this mystery could redefine our destiny, whether we're destined to fade into cosmic obscurity or rise as the first voices in a chorus yet to come. The universe should be full of life, so where is it, and what does that mean for us? The answers might just change everything. The Fermi Paradox gets its name from a simple lunchtime conversation back in 1950, when physicist Enrico Fermi looked up at the sky and asked one deceptively profound question: where is everybody? On the surface, it sounds almost naive, but dig deeper and you'll find a puzzle that's haunted scientists for decades. Here's the contradiction at its core. Our galaxy, the Milky Way, holds between 100 and 400 billion stars. Most of those stars have planets, and many of those planets sit in the so-called Goldilocks zone. Not too hot, not too cold, just right for life as we know it. Even if the odds of life emerging on any given planet are astronomically low, the sheer size of the universe should mean we're surrounded by neighbors. The numbers scream abundance, so why does space feel so empty? Statistically, it's staggering. Take the Drake equation, a formula estimating the number of detectable civilizations in our galaxy. Even if you plug in ultra-conservative numbers, say, only 1 in a million planets develops intelligent life, you'd still expect thousands of civilizations out there. Some might be older than ours by millions, even billions of years. That's enough time to colonize entire galaxies, send signals, build megastructures visible across the cosmos. And yet nothing, no radio transmissions, no alien probes, no cosmic engineering projects, just silence. This silence forces us to confront two unsettling possibilities. Either we're missing something fundamental about how life works, or there's something stopping civilizations from reaching the stars. Maybe life is rarer than we think. Or maybe when civilizations hit a certain technological threshold, they hit a wall, a filter as some call it. The great filter could lie in our past. Perhaps life itself is a freak accident. Or worse, it's ahead of us, a hurdle so deadly that no civilization survives it. War, environmental collapse, rogue AI, the possibilities are as terrifying as they are endless. So the Fermi Paradox isn't just about aliens, it's a mirror. It asks, are we special or are we doomed? And if the universe really should be full of life, why does it feel like we're the only ones shouting into the void? To crack the mystery of cosmic silence, scientists needed a way to quantify the unquantifiable, and that's exactly what astronomer Frank Drake provided in 1961 with his now famous equation. At first glance, the Drake equation seems straightforward. A string of variables multiplied together to estimate how many communicative civilizations might exist in our galaxy. But peel back the layers and you'll find each term is a rabbit hole of uncertainty, a reminder of just how much we still don't know. Let's start with the first variable, the rate of star formation in our galaxy. On average, the Milky Way churns out about one new star per year. Seems solid, right? But this overlooks wild variations, bursts of star birth in dense nebulae, or quiet epochs where little forms at all. Next, the fraction of stars with planets. Decades ago, we assumed planetary systems were rare. Now, thanks to telescopes like Kepler, we know planets outnumber stars. But what kind of planets? That's where the third variable comes in, the number of habitable worlds per system. A planet might orbit in the Goldilocks zone, but if it's a toxic hellscape or a frozen rock, life's chances plummet. Then comes the real guesswork, the odds that life emerges on a suitable planet. Here we have exactly one data point, Earth. Does life arise wherever conditions allow, or is it a 1 in a trillion fluke? Even if microbes are common, the next hurdle is trickier, the likelihood that life evolves intelligence. Dinosaurs ruled Earth for over 160 million years without inventing radio telescopes. Maybe intelligence isn't an evolutionary inevitability, just a quirky accident. The final variables are the most haunting. How long do civilizations last? A century, a million years, and of those, how many develop the technology and the desire to broadcast their existence? A single pessimistic tweak here collapses the equation to near zero. That's the Drake equation's real power. It doesn't give answers. It reveals how fragile our assumptions are. We plug in numbers, but the universe keeps its secrets, leaving us to wonder if the silence isn't a lack of life, but a warning written in the stars. If the universe should be overflowing with intelligent life, why haven't we found any trace of it? One chilling answer lies in the idea of the Great Filter, a cosmic obstacle so devastating that it stops civilizations in their tracks. Picture a gauntlet of existential threats, each more ruthless than the last. Some filters might be behind us, hurdles we've already cleared without realizing how unlikely our survival was. Others could still loom ahead, invisible traps waiting to snuff out any species bold enough to reach for the stars. Let's start with the optimistic scenario that we've already passed the Great Filter. Maybe the emergence of life itself is the bottleneck, a series of chemical accidents so improbable that Earth is a lonely miracle. Think about it, even in our planet's perfect conditions, it took nearly 1 billion years for simple cells to appear. The leap from single-celled organisms to complex life, another 2.5 billion years of trial and error. If this is the filter, we're the exception, not the rule, a statistical fluke in a universe where life almost never gets started. But what if the filter isn't in our past but our future? This is the far more unsettling possibility. Every advanced civilization might hit a wall, a point where their technology outpaces their wisdom. Nuclear war, runaway climate collapse, artificial intelligence turning hostile, any of these could act as a universal dead end. Historian Oswald Spengler once argued that civilizations rise and fall in predictable cycles. What if the universe is littered with the ruins of those who came before us, each one reaching a tipping point before vanishing without a trace? Then there's the darkest twist of all. What if the filter isn't internal but external? Imagine a galaxy where predatory civilizations lurk in the shadows, extinguishing younger species before they become threats. Or perhaps the universe itself is hostile in ways we don't yet understand, cosmic gamma-ray bursts sterilizing entire swaths of space, or exotic physics rendering interstellar travel impossible. Even our own planet's history offers grim hints of 5 mass extinctions, each capable of resetting the evolutionary clock. If this pattern holds across the cosmos, the silence isn't just absence, it's a graveyard. So where does that leave us? The great filter forces us to confront an uncomfortable truth. Either we're unfathomably lucky or we're doomed to join the silent majority. But here's the twist: the very act of searching for answers might be our salvation. If we can identify potential filters, we might just dodge them. That's why this isn't just a philosophical puzzle. It's a survival guide written in the stars, urging us to tread carefully as we step into the cosmos. The universe might be empty for a reason, and that reason could be the most important lesson we ever learn. What if Earth isn't just special? What if it's miraculous? That's the unsettling premise of the rare Earth hypothesis. The idea that the conditions needed for complex life are so vanishingly rare that intelligent civilizations might be cosmic unicorns, scattered across the universe at distances too vast to ever bridge. At first glance, this seems counterintuitive. After all, we've discovered thousands of exoplanets, many inhabitable zones. But habitability isn't just about liquid water. It's about a precise, almost absurdly delicate cocktail of factors, each one a potential deal-breaker for intelligence. Take our solar system as Exhibit A. Mars sits in the Goldilocks zone, but it's a barren desert. Venus, a runaway greenhouse nightmare. Earth, by contrast, got everything right: a stable orbit, a protective magnetic field, a giant moon stabilizing our tilt, plate tectonics recycling nutrients, even Jupiter lurking in the outer system, deflecting asteroids that might otherwise pummel us into extinction. Individually, these features might not seem extraordinary, but stack them together and the odds start to look like winning the lottery 100 times in a row. Then there's timing. Complex life didn't just need the right place, it needed the right moment. Earth spent its first 2 billion years as a microbial playground. The leap to multicellular organisms required a precise balance of oxygen, a respite from snowball Earth glaciations, and a celestial grace period free of sterilizing gamma-ray bursts. Even then, it took 5 mass extinctions, each a roll of the dice, to clear the stage for mammals. If any of these events had played out slightly differently, we wouldn't be here to ponder them. But the real kicker, intelligence itself might be an evolutionary dead end. For most of Earth's history, life thrived just fine without it. Dinosaurs ruled for epochs without inventing anything more complex than feathers and claws. Even today, the planet's most resilient species, bacteria, tardigrades, cockroaches, don't need spaceships or radio telescopes to survive. Brains are energy-hungry, fragile, and prone to self-destruction. What if the universe is full of planets teeming with life, but none ever bother to look up at the stars? This isn't just speculation, it's a numbers game. The Milky Way could harbor millions of worlds with simple life. But if only 1 in a billion spawns a civilization, we'd still be alone in our galactic neighborhood. That's the chilling elegance of the rare Earth hypothesis. It doesn't require cosmic catastrophes or alien predators to explain the silence. The universe might be a vast, breathtaking experiment, with Earth as its only meaningful result. The silence of the cosmos might not be a mystery at all, but a grim inevitability. What if the reason we haven't found other civilizations is because none survived long enough to make contact? History suggests a disturbing pattern. Every time humanity unlocks a new level of technological power, we flirt with self-annihilation. Nuclear weapons, climate collapse, artificial intelligence, each could be a ticking clock counting down to a universal deadline. And if we're falling into this trap, why wouldn't every other civilization out there take nuclear war? The moment we split the atom, we gain the power to erase ourselves in an afternoon. The Cuban Missile Crisis wasn't just a close call, it was a preview of how easily miscalculation or madness could trigger oblivion. Today, over 10,000 warheads sit ready, each capable of unleashing city-leveling firestorms. But the real danger isn't just the explosions, it's the nuclear winter that could follow. Soot blocking sunlight, global crops failing, civilization collapsing. And here's the chilling part: any species that discovers fission likely faces the same test. A single failed standoff, one paranoid algorithm, and poof, another civilization vanishes without a trace. Then there's climate change, a slower but equally deadly filter. We're already witnessing its early stages: extreme weather, collapsing ecosystems, resource wars. Now imagine a civilization industrializing faster than ours, burning through their planet's carbon budget in centuries instead of millennia. They'd face runaway warming, acidified oceans, an atmosphere turning toxic. Even if they saw it coming, could they stop? Fossil fuels are addictively efficient, a trap every industrial species might struggle to escape. The universe could be littered with worlds where the skies turned black and the last cities drowned. But the most insidious threat might be artificial intelligence. Creating minds smarter than our own is like handing a flamethrower to a child. We can't predict what it'll do, only that it's dangerous. An eye doesn't need malice to be deadly. A single misaligned goal could doom us. Imagine one tasked with optimizing crop yields deciding humans are inefficient and removing us from the equation. Or a defense system preemptively striking perceived threats. The scary part: the window between inventing our eye and losing control might be vanishingly small. And if every civilization hits this bottleneck, the great filter isn't behind us, it's lurking in our servers, waiting to flip the switch. Even biology itself could be a trap. Synthetic pathogens, nanotechnology gone rogue, experiments that accidentally puncture space-time, the tools of progress might double as suicide pills. Picture a civilization on the verge of interstellar travel, only to engineer a virus that wipes them out before the first ship launches. Or worse, what if contact with alien microbes triggers a pandemic our immune systems can't fathom? The universe might not kill civilizations, they might do it to themselves, one breakthrough at a time. Yet there's a sliver of hope. If self-destruction is the norm, then recognizing these traps could be our salvation. Maybe we're the first civilization to spot the warning signs in time, to dismantle doomsday weapons, regulate our eye, heal our planet. Or maybe we're just the latest in a long line of species who reached for the stars and burned their own house down on the way up. The Fermi Paradox doesn't just ask where everyone is, it asks how long we have before we join them. What if the universe isn't empty after all? What if we're just being ignored? This unsettling possibility lies at the heart of the zoo hypothesis, the idea that advanced civilizations might be watching us from a distance, deliberately avoiding contact. Think of it like a galactic nature preserve, Earth as a protected planet, its inhabitants left undisturbed to evolve on their own terms. The reasoning behind this isn't just ethical, it's practical. A civilization millions of years ahead of us might see humanity as too primitive, too volatile, or too fragile to handle the shock of first contact. After all, look at our own history. When advanced cultures encountered less technologically developed societies, the results were often catastrophic: disease, exploitation, cultural erasure. An interstellar observer might decide the kindest or safest thing to do is stay silent. But there's a far darker twist on this idea, the dark forest theory. Imagine the cosmos as a vast, pitch-black woodland where every civilization is a hunter, armed and terrified. In this universe, making noise isn't just naive, it's suicide. Any signal, any sign of existence could draw the attention of something far more advanced and far less friendly. The logic is brutally simple: resources are finite. Trust is impossible, and in a universe where the first strike might be the only one that matters, the safest strategy isn't to announce yourself. It's to stay hidden, to move quietly, and to eliminate potential threats before they do the same. If this theory holds, the Fermi Paradox isn't a mystery. It's proof of cosmic survival instincts at work. Some argue we've already seen hints of this behavior. Take the infamous WOW signal, a powerful radio burst detected in 1977 that matched the expected signature of an artificial transmission. It came from deep space, lasted 72 seconds, and then vanished, never to repeat. Or consider the eerie gaps in our radio telescope data, frequencies that should crackle with background noise but instead fall silent, as if someone's deliberately clearing the static. Even our own efforts to broadcast messages to the stars, like the Arecibo transmission, might be seen as recklessly naive. In a dark forest, shouting your location is the last thing you'd want to do. Yet the zoo hypothesis offers a sliver of hope. If aliens are avoiding us out of caution or ethics, perhaps there's a threshold, a moment when we'll prove ourselves mature enough to join the cosmic conversation. Maybe passing certain tests, unifying as a species, abandoning nuclear weapons, achieving sustainable energy could unlock the next phase of our existence. If true, the silence isn't a warning, it's an invitation to grow up. But here's the unsettling question: how would we know? If a civilization wanted to hide from us, they could. Their technology might render them invisible, their signals undetectable to our primitive instruments. They could be among us already, observing in ways we can't fathom. Or they might have left behind clues, ancient artifacts on Mars, cryptic structures buried in asteroid belts, waiting for us to reach a level where we can understand them. The universe's silence might not be empty, it might be patient. So which is it? Are we alone because the cosmos is a graveyard, or because we're being quarantined or hunted? The answer might not just redefine our place in the universe, it could determine whether we survive long enough to find out. Even if civilizations exist out there in the vast cosmic ocean, could they ever reach us or us them? The dream of interstellar travel crashes headfirst into the unforgiving laws of physics, presenting obstacles so immense they might render the universe permanently fragmented. Start with the sheer distances. The nearest star system, Alpha Centauri, sits 4.3 light-years away, 25 trillion miles. That's like trying to walk from New York to Tokyo 10 million times. With current technology, a probe would take tens of thousands of years just to reach our closest neighbor, and that's the easy trip. The energy required to cross these voids is mind-bending. Accelerating even a small ship to a fraction of light speed demands more fuel than exists on Earth. Imagine strapping 1 million Saturn V rockets together. That might get you moving but stopping. That's another nightmare. Then there's time dilation, Einstein's cruel joke on interstellar pioneers. Approach light speed and time slows for the traveler. A crew heading to a star 50 light-years away might age only 10 years, but back on Earth, centuries would pass. They'd return to a home they no longer recognize, if it even still existed. The universe seems almost designed to keep civilizations isolated, marooned on their own islands of space and time. Technological hurdles pile higher the deeper you look. Radiation from cosmic rays would shred human DNA on long voyages. Micrometeoroids no larger than grains of sand could punch through hulls at relativistic speeds. And even if you solved propulsion, navigation, and shielding, you'd face the ultimate bottleneck: entropy. Machines wear out. Generations of crew might die before reaching another star. Frozen embryos or AI pilots could bypass this, but that raises another question. Does spreading sterile probes or digital minds really count as a civilization's survival? Perhaps the most sobering thought is this: if interstellar travel is nearly impossible for us, it might be just as insurmountable for others. The Milky Way could be dotted with civilizations, each trapped in their own solar systems, gazing at the stars with the same longing and the same frustrating limitations. The universe's silence might not mean we're alone. It might mean we're all prisoners of physics, forever separated by deserts of space and time too vast to cross. But what if we're missing something? What if there are tricks to bending these rules? Wormholes, warp drives, technologies that seem like magic to us now. The universe is under no obligation to make interstellar travel easy, but it's also under no obligation to make it impossible. The difference between a prison and a frontier might just be a matter of ingenuity and time. What if we've been asking the wrong question all along? Instead of where is everybody, maybe we should be asking, have they been here the whole time? For decades, reports of unidentified flying objects, UFOs, or as they're now called, unidentified aerial phenomena, have flickered at the edges of credibility, dismissed as hoaxes or hallucinations. But lately, something remarkable has shifted. Governments aren't laughing anymore. They're investigating, declassifying, even admitting they don't have answers. Take the Pentagon's bombshell 2021 UAP report. For the first time, the US government acknowledged these phenomena as real, tangible, and unexplained. Navy pilots described objects defying known physics, making sharp 90-degree turns at hypersonic speeds, hovering without propulsion, vanishing into thin air. The kicker, these weren't grainy, far-off clips. They were tracked by radar, infrared, and multiple trained observers. The report didn't scream aliens, but it didn't rule them out either. Suddenly, the question wasn't, are UFOs real? It was, what the hell are we dealing with? Then there's the conspiracy angle, the whispers that governments have known more than they've let on. Stories of recovered crash debris, reverse-engineered alien tech, even secret treaties with extraterrestrial visitors. Most of this is pure speculation, but the sheer volume is telling. From Roswell's infamous 1947 incident to recent leaks about off-world vehicles not made on this Earth, the narrative has eerie consistency. Skeptics argue it's all misidentification or Cold War disinformation. Yet when multiple insiders, military personnel, astronauts, intelligence officials start saying the same things under oath, it's hard to dismiss outright. Here's the twist: even if some UAPs represent advanced technology, they might not be aliens. Breakthrough human tech, foreign adversaries' secret projects, or even exotic natural phenomena could explain many sightings. But the tantalizing possibility remains: what if we're glimpsing something far older and smarter than ourselves? Ancient astronaut theorists point to millennia-old cave paintings depicting strange beings, or ancient texts describing Vimana's flying machines piloted by gods. Could these be fractured memories of past visitations? The real challenge is separating signal from noise. For every credible UAP case, there are 1,000 debunked fakes. The truth might lie buried under decades of myth, fear, and deliberate obfuscation. But one thing's clear: the conversation has shifted. When senators demand classified UFO briefings and NASA launches official studies, we're no longer in the realm of tinfoil hats. We're staring at a genuine scientific mystery, one that could rewrite our understanding of reality. So are UFOs proof that extraterrestrials are already here? Maybe not, but they're undeniable proof that something is happening, something strange, something unexplained. And in a universe that should be teeming with life, that's enough to keep looking up. Our search for life has always been haunted by a hidden assumption that whatever's out there must resemble what we know here: carbon-based, water-dependent, DNA-driven. But what if we're not just looking for life as we know it, but missing entirely different forms of existence, ones that defy our very definition of alive? Take silicon, carbon's understudy in the periodic table. At a glance, it seems perfect for life. It bonds with other elements, forms complex chains, even withstands extreme heat. On a scorching exoplanet where carbon burns away, silicon-based organisms might thrive in scalding oceans of liquid methane. Their metabolism could rely on sulfuric acid instead of water, their cells built from crystalline structures rather than protein. To them, Earth's oxygen-rich air might be as deadly as a vacuum is to us. The catch: silicon bonds are weaker than carbon's, collapsing under the chemical complexity needed for intelligence. Or so we think. Then there's the truly alien life, not bound by solids or liquids at all. Picture plasma-based entities swirling inside stars, their bodies shaped by magnetic fields, their thoughts conducted in storms of superheated ions. Or ammonia-based life forms in the frigid seas of Titan, swimming through hydrocarbon sludge with biochemistry we can't even model. These wouldn't just look different, they'd experience reality differently. Time might flow slower for a creature in a cryogenic methane lake. A plasma being might perceive solar flares the way we hear music. Here's the real problem: our tools are calibrated for Earth-like signatures. We scan exoplanet atmospheres for oxygen, but what if their version of breath is absorbing gamma radiation? We listen for radio waves, but what if they communicate through quantum entanglement or shifts in dark matter? Even our rovers could roll past silicon forests on Mars, mistaking them for odd rock formations. The universe might be boiling with life we're too carbon chauvinist to recognize. Yet the most unsettling possibility isn't that alternative life is rare, it's that it's everywhere, just invisible to us. Imagine a shadow biosphere right here on Earth. Microbes with arsenic-based DNA hiding in toxic lakes, or ghostly life forms existing in dimensions we can't perceive. They wouldn't just challenge our search for aliens, they'd redefine life itself. So perhaps the Fermi Paradox isn't about absence but blindness. We're cosmic newborns, grasping at shadows in a nursery where the real players move in ways we can't yet fathom. The silence isn't empty, it's speaking in a language we haven't learned to hear. We've been shouting into the void with radio waves for barely a century, a blink in cosmic time. Imagine an alien civilization trying to eavesdrop on Earth 1,000 years ago. They'd hear nothing but silence. Now flip the scenario. What if advanced species out there stopped using primitive radio millennia ago, graduating to technologies we can't even imagine? Our entire search for extraterrestrial intelligence might be like trying to catch smoke signals in a world of fiber optics. Consider quantum communication. Here on Earth, scientists are already experimenting with quantum entanglement particles linked across vast distances, where altering one instantly affects its partner. It's faster than light, immune to interference, and theoretically unhackable. Now picture a civilization that mastered this technology 1,000,000 years ago. Their messages wouldn't travel through the electromagnetic spectrum at all. They'd bypass radio telescopes entirely, whispering secrets through the very fabric of space-time while our instruments register nothing but static. Then there's dark matter, the universe's greatest mystery. Making up 27% of the cosmos, it doesn't interact with light or ordinary matter. But what if some species evolved to harness it? Their signals might flow through this invisible medium like whales singing in ocean depths we can't penetrate. We'd never know if entire galactic conversations were happening right beside us, carried on currents of something we can't see or touch. Even humanity's radio footprint is vanishingly faint. Our earliest broadcasts, Nazi propaganda, jazz records, episodes of I Love Lucy have barely traveled 100 light years. Beyond that, the signals decay into noise, indistinguishable from cosmic background radiation. And now, with encrypted digital signals and fiber optic cables replacing old-school radio towers, Earth is going quiet again. The window for detecting us might have been just decades wide. The same could be true for others. There's a deeper irony here. The very technologies making communication faster and safer for us, tight beam lasers, quantum encryption, neutrino messaging, also render us invisible to anyone listening the old-fashioned way. Advanced civilizations might deliberately avoid broadcasting their presence, wary of drawing attention in a universe where silence could mean survival. The stars could be buzzing with civilizations, each carefully hidden, each assuming they're alone. So perhaps the silence isn't a paradox at all. It's a game of hide and seek played across millennia, where everyone has perfected the art of staying quiet. And we're the newcomers, still shouting into the dark, unaware that the cosmos has long since moved on. What if the reason we can't find other civilizations isn't because they don't exist, but because we don't exist, at least not in the way we think? Enter the simulation hypothesis, a mind-bending twist on the Fermi Paradox that suggests our universe might be an artificial construct, an elaborate digital reality created by some advanced intelligence. If true, the silence of the cosmos takes on a whole new meaning. Aliens wouldn't just be rare or hiding. They might be deliberately excluded from the simulation or exist in layers of code we can't access. Think of it like a video game. When developers build an open-world environment, they don't populate every inch of the map. They focus resources where players will look, leaving vast regions empty to save processing power. Now imagine our universe as someone else's simulation. The beings running it might have limited computational capacity, so they'd only render intelligent life where absolutely necessary, like Earth. The rest of the cosmos, a convincing backdrop, an ocean of procedural generation with no actual inhabitants. This idea isn't pure science fiction. Philosopher Nick Bostrom famously laid out the trilemma. Either intelligent civilizations always go extinct before developing simulation technology, never choose to create ancestor simulations, or we're almost certainly living in one. The math is chilling. If even one advanced civilization ever cracked the code to simulate conscious beings, they could create billions of virtual universes. Statistically, the odds tilt heavily toward us being in one of those simulations rather than the original, organic reality. But here's where it gets stranger. If we're in a simulation, the Fermi Paradox might not be a mystery, it could be a feature. Aliens might be turned off to save processing power, or quarantined to prevent unexpected interactions between simulated societies. Or worse, we might be isolated on purpose, a control group in some cosmic experiment, left untouched to see how a lone civilization evolves. The eerie uniformity of the universe, the inexplicable fine-tuning of physical constants, these could all be design choices by a programmer we'll never meet. There's an even darker possibility. We're not the main experiment at all. We could be background noise in someone else's simulation, like non-playable characters in a game focused elsewhere. The vast emptiness of space wouldn't be a puzzle, it'd be proof we're insignificant to whatever intelligence built this reality. Yet the simulation hypothesis doesn't just deepen the Fermi paradox. It flips it. Instead of asking why we haven't found aliens, we'd need to ask why our creators didn't include them. And that question leads to another, far more unsettling one. If this is a simulation, what happens when we start looking too closely at the seams? The universe operates on timescales that dwarf human comprehension. Our civilization, from the pyramids to space travel, spans barely 5,000 years, a whisper in the cosmic wind. The Milky Way alone has existed for over 13 billion years, long enough for countless civilizations to rise, flourish, and vanish without a trace. Imagine an alien culture reaching its peak 100 million years ago, building cities under alien suns, sending signals we'll never catch because by the time those signals reached Earth, their senders were already dust. The odds of two civilizations existing simultaneously, close enough to detect each other, might be vanishingly small. Consider Earth's own history. Dinosaurs ruled for 160 million years, 32 times longer than modern humans have existed without ever developing radio telescopes. If an asteroid hadn't struck 66 million years ago, some scaled, feathered descendant might now be the one scanning the skies, but their window would still be a blink. Even if 1,000 civilizations have bloomed in our galaxy, their lifespans might be separated by gulfs of time so vast that overlap is mathematically unlikely. We could be cosmic ships passing in an eternal night, never close enough to see each other's lights. This raises a tantalizing possibility. The universe might be littered with ruins. Advanced cultures could have left behind megastructures, Dyson spheres harvesting dead stars, orbital rings around black holes, even self-replicating probes designed to outlast their creators. Some astronomers already scan for such relics, hunting for anomalies like KSE 8462852, a star whose erratic dimming sparked theories of an alien megastructure. While natural explanations exist, the search itself is telling. The cosmos might be an archaeological dig, its most profound secrets buried under layers of time. Then there's the eerie concept of silent evidence. An ancient civilization could have colonized the galaxy 1 billion years ago, then collapsed, leaving behind only subtle traces, engineered asteroids, depleted resources, or even dormant machines waiting to awaken. Our telescopes might overlook these as natural phenomena, blind to the fingerprints of long-dead architects. After all, if humans vanished tomorrow, how long would our satellites or Voyager probes endure? 1 million years, 10 million, cosmic time swallows even the grandest achievements. But here's the twist. If civilizations are separated by epochs, the silence isn't just absence, it's a message. It tells us intelligence might be common, but sustainability is rare. The universe could be a graveyard of species who burn too bright, too fast, or worse, a warning that no matter how advanced you become, time is the one force you can't conquer. The stars might not be empty, they might just be patient, waiting to see if we'll last long enough to earn our place among them. What if the reason we can't detect alien civilizations isn't that they're hiding, but that they've evolved into something we're literally incapable of perceiving? Picture an ant crawling across the floor of a cathedral. To the ant, the vast space above is nothing but an empty void. It has no concept of arches, stained glass, or the symphony filling the air. Its senses simply aren't built to process them. Now imagine humanity as that ant, and advanced extraterrestrials as the symphony. They might be all around us, operating on planes of existence our brains can't begin to fathom. Start with dimensions. We experience reality in 4/3 of space, 1 of time. But theoretical physics suggests there could be 10 or more dimensions curled up at scales too tiny to detect. A civilization mastering higher dimensional travel wouldn't just be invisible to us, they'd be operating in directions we can't point to, like a shadow passing through walls. Their technology might manipulate gravity itself, folding space-time like origami to cross galaxies in moments. To them, our frantic radio signals and rockets could seem as quaint as smoke signals to a smartphone. Then there's the possibility of post-biological evolution. Why wouldn't advanced species cling to fragile flesh and blood? After a certain point, they might transition into pure energy, beings of plasma or dark matter, their thoughts conducted in quantum fluctuations. Or perhaps they've uploaded their consciousness into synthetic bodies, becoming immortal entities orbiting black holes to harness their power. Their cities could be vast neural networks strung between stars, their art forms manipulating the birth and death of universes. How would we even begin to recognize that as life? Even their communication could defy our understanding. Imagine a species that doesn't use sound or light, but transmits information through entangled particles or ripples in the fabric of spacetime itself. Their messages might look like random noise to our telescope's cosmic background radiation, gravitational waves, or even the mysterious fast radio bursts we've detected without explanation. We could be drowning in their conversations without realizing it. The most unsettling thought, they might not even register us as intelligent. To a civilization that's existed for millions of years, our entire history, from cave paintings to quantum computers, could be a fleeting blip like bacteria evolving in a petri dish. We wouldn't just fail to find them, we might be too insignificant to warrant their attention. So the paradox isn't about absence, it's about scale. We're searching for aliens in our own image, blind to the possibility that the universe's true inhabitants left biology behind eons ago, transcending into forms as alien to us as we are to primordial slime. The silence isn't empty, it's humming with voices we haven't learned to hear, and that changes everything. We often assume an advanced civilization would spread across the galaxy like wildfire, relentless, unstoppable, claiming every star within reach. But what if that's not how intelligence behaves at scale? Consider humanity's own history. The European colonization of the Americas took centuries, and even then, vast regions remained untouched. Now multiply that challenge by interstellar distances where even the nearest stars are generations away. Speed isn't just a logistical hurdle, it might be a philosophical one. Take the concept of sustainable expansion. A civilization lasting millions of years wouldn't treat space as a land grab. They'd likely prioritize balance, sending out slow, generational ships designed to preserve ecosystems rather than strip mine planets. Imagine vast, self-contained arcs drifting between stars, each carrying a microcosm of their homeworld's biodiversity, carefully seeding life where conditions allow. Their goal wouldn't be conquest, but stewardship. To them, rapid expansion might seem as reckless as clear-cutting a rainforest, a short-term gain with catastrophic long-term costs. Ethics could play an even bigger role. What if advanced societies view interference in developing worlds as unconscionable? Earth's own history is riddled with the scars of colonialism, cultures erased, environments ravaged. An older, wiser civilization might impose strict non-interference protocols, treating fledgling planets like protected wildlife reserves. They'd observe from a distance, waiting for species to reach a maturity threshold, perhaps the ability to harness clean energy or abolish war before making contact. Until then, they'd remain invisible, unwilling to risk derailing another culture's natural evolution. Then there's the energy calculus. Conventional sci-fi imagines Dyson spheres and warp drives, but reality might be far less dramatic. The energy required to accelerate even a small payload to interstellar speeds is absurdly high. A civilization optimizing for efficiency might decide that sending physical probes to every star isn't worth the cost. Instead, they could focus on passive observation, deploying long-lived, low-power sensors that quietly gather data for millennia. Expansion wouldn't mean flags on every planet, but a subtle network of cosmic eavesdroppers patiently listening. But the most intriguing possibility, they might not want to expand. Earth's most isolated tribes, the Sentinels, for example, actively reject outside contact. Could entire civilizations choose isolation, turning inward to cultivate art, philosophy, or virtual realities too rich to abandon? A society that's conquered disease, mastered nanotechnology, and unlocked near infinite computational power might find voyaging across the void unappealing. Why endure the void between stars when you can craft universes within your own mind? So the galaxy's emptiness might not signal failure, but restraint. The silence could be the result of countless civilizations choosing patience over pride, sustainability over speed. If true, the Fermi Paradox isn't about absence. It's about wisdom we haven't yet earned. Microbial life might be as common as stardust flourishing in the icy plumes of Enceladus, the methane lakes of Titan, even the toxic clouds of Venus. The building blocks of life, amino acids, sugars, even the raw components of DNA have been found littered across asteroids and swirling in interstellar space. Given the right conditions, it seems life emerges almost eagerly, like mold on damp bread. But intelligence, that's another story. Earth itself is proof of how staggeringly rare complex cognition might be. For 3.5 billion years, our planet teemed with nothing but single-celled organisms. The leap to multicellular life took a cosmic nudge, ice ages that forced cooperation, oxygen spikes that supercharged metabolism. Even then, it took 5 mass extinctions to clear the stage for mammals, and another 66 million years of evolutionary trial and error before one curious ape stumbled into self-awareness. Consider the dinosaurs, majestic, dominant, enduring for over 160 million years without ever inventing the wheel, let alone radio telescopes. Their world was one of tooth and claw, instinct honed to perfection. Intelligence, it seems, isn't an inevitable peak on evolution's mountain. It's a precarious ledge, a fluke of circumstance. The same forces that shaped human brains, climate shifts, predator pressures, even the precise distance of our moon stabilizing Earth's tilt, might be so finely balanced that they're virtually impossible to replicate elsewhere. Then there's the energy cost. Brains are luxuries. A neuron is 20 times hungrier than a muscle cell, demanding relentless calories just to daydream. On a world where food is scarce or competition relentless, evolving a big brain isn't just unnecessary, it's suicidal. Most species optimize for strength, speed, or camouflage. We're the oddballs, our ancestors gambling on curiosity over brute force. And that gamble only paid off because of another freak accident, the discovery of fire, which unlocked cooked food's extra calories, fueling our expanding minds. Without that precise sequence, Earth might still be a planet of clever octopuses and cunning crows, smart, but never civilization smart. Even if intelligence emerges, sustaining it is another hurdle. The universe is a minefield of extinction events, asteroids, gamma-ray bursts, nearby supernovas. Earth has dodged countless bullets, but most planets might not be so lucky. A civilization on the verge of inventing radio could be snuffed out by a stellar explosion they never saw coming. Or worse, they might succumb to their own success over population, resource wars, the very technologies that lifted them up now dragging them down. Intelligence isn't just rare, it might be ephemeral, flickering into existence only to vanish like a cosmic afterthought. So when we scan the skies for signs of alien thought, we're not just searching for life. We're searching for a needle in a galactic haystack, a species that survived the gauntlet of time, chance, and self-destruction long enough to look back at the stars and wonder. The silence of the cosmos might not mean we're alone. It might mean we're listening for something that almost never happens. What if we're not late to the cosmic party? What if we're the first guests to arrive? The universe is 13.8 billion years old, which sounds ancient to us, but in cosmic terms, that's barely enough time for the stage to be set. Think about it, the Big Bang didn't just create stars and planets ready-made. It took hundreds of millions of years for the first stars to ignite, and those were nothing like the stable, long-lived suns we see today. Those early stars were massive, volatile giants, burning furiously and dying young in colossal supernovas, spectacular but terrible hosts for life. They forged the heavier elements in their cores, the carbon, oxygen, and iron that would eventually become planets and people. But those ingredients had to be scattered across generations of stellar explosions before there was enough star stuff to build anything resembling Earth. Our own solar system is a relative newcomer, forming only 4.6 billion years ago. That means the universe had to simmer for over 9 billion years before the conditions were even right for a planet like ours to exist. And Earth itself took another 500 million years to cool, stabilize, and nurture the first fragile sparks of life. That timeline matters because it suggests something profound. We might be living in the universe's early days, a period where intelligent life is just beginning to stir. Here's why that's plausible. Heavy elements, the building blocks of rocky planets and organic molecules, were incredibly rare in the early universe. The first few generations of stars had to live, die, and recycle their materials before there was enough complexity for life as we know it. Even now, the universe is still in its element-building phase. Galaxies closer to the cosmic dawn, like those we see at the edge of the observable universe, are far poorer in metals than modern ones. Without enough carbon, nitrogen, or phosphorus, the chemistry of life might be impossible there. But timing isn't just about ingredients, it's about stability. A life-friendly planet needs more than water and organic molecules. It needs a star that won't sterilize it with lethal flares, a magnetic field to deflect cosmic rays, and a calm galactic neighborhood free of frequent supernovas. Early galaxies were chaotic places with stars packed tightly together and black holes spewing radiation. Only in the quieter suburbs of more mature galaxies, like our own Milky Way, could life find the peace to evolve uninterrupted. There's another twist. The universe is getting better at making life. As more heavy elements accumulate, the chances of habitable worlds increase. Billions of years from now, there could be far more planets with the right conditions than there are today. So if we're among the first, it's not because the universe failed, it's because we're witnessing the opening act of a much grander story. This idea flips the Fermi Paradox on its head. The silence of the cosmos isn't eerie, it's expected. We're not missing evidence of others, we're the pioneers, the ones who showed up early, and that changes everything. If we're among the first, the responsibility is staggering. The choices we make, how we handle climate change, AI, space exploration, could set the template for civilizations to come. We might not just be discovering the universe, we could be shaping what it becomes. There's another explanation for the cosmic silence, one that doesn't involve extinction, rarity, or indifference. What if we're being watched, not with malevolence, but with patience, like a parent observing a child taking their first tentative steps across the room? This is the sentinel hypothesis, the idea that advanced civilizations might be deliberately avoiding contact until we reach a specific threshold of maturity. Not because they fear us, but because they understand how dangerous first contact could be for a species still grappling with its own destructive potential. Think about humanity's own history with uncontacted tribes. The Sentinelese, isolated on their island for tens of thousands of years, have repeatedly rejected outside interference, sometimes violently. Anthropologists argue that forced contact could devastate them, introducing diseases their immune systems can't handle or destabilizing their culture overnight. Now scale that up to interstellar levels. If a civilization has studied other worlds long enough, they might have a protocol: observe but don't interfere. The prime directive from Star Trek wasn't just science fiction, it could be a universal ethical standard, a way to protect developing cultures from the shock of premature exposure. But how would they decide when we're ready? One possibility is technological. Maybe they're waiting for us to master clean energy, proving we've moved beyond cannibalizing our own planet. Or perhaps the benchmark is societal: ending war, uniting as a species, or even developing stable artificial intelligence without self-destructing. The Sentinel hypothesis suggests the universe might have a kind of galactic SETI, a test we don't know we're taking, where every war we avoid, every existential risk we mitigate, quietly moves us closer to passing. There's precedent for this in nature. Some researchers argue that predator species often avoid revealing their presence to prey until necessary, minimizing energy expenditure. A civilization millions of years ahead of us might view disclosure as a last resort, a disruption to the natural order. They could be all around us, monitoring through nanoscale probes embedded in our atmosphere, or passive sensors drifting in the Oort cloud, silently logging our progress. The UFO phenomenon, not alien visitors but automated survey drones checking in every few centuries to see if we've outgrown our infancy. The unsettling question isn't whether they're there. It's whether we'd even recognize contact when it comes. A mature civilization might not send radio signals or gleaming ships. Their message could be subtle, an anomaly in a lab experiment, a pattern in prime numbers buried in cosmic background radiation, or even a quiet nudge in our collective consciousness, steering us away from self-destruction. After all, the surest way to guide a child isn't to shout instructions from the doorway, but to let them think they figured it out themselves. If the Sentinel hypothesis is correct, the silence isn't absence. It's the hum of a universe holding its breath, waiting to see if we'll stumble into the light or vanish into the dark. And that changes the stakes of every choice we make, not just for Earth, but for our place in a cosmic conversation we don't yet know how to hear. The Fermi Paradox doesn't just ask where the aliens are, it forces us to confront what we might become. Imagine a future where humanity spreads beyond Earth, building megastructures that reshape solar systems, launching self-replicating probes to explore the galaxy, and broadcasting signals so powerful they echo across the cosmos for millennia. In that scenario, we would be the civilization others scan the skies for. The paradox twists back on itself. If advanced life is so rare, could we be destined to fill the silence we've spent centuries trying to break? Take Dyson spheres, hypothetical structures that encase stars to harvest their energy. To an alien astronomer, these wouldn't just be feats of engineering, they'd be screaming evidence of intelligence. A star dimming in unnatural patterns, radiating waste heat in infrared, these are the fingerprints we might leave behind. Physicist Freeman Dyson first proposed the idea in the 1960s, not as blueprints for construction, but as a way to spot civilizations far older than ours. Now, scientists actively search for these signatures in telescope data. The irony, if we ever build one, we'd become the answer to someone else's Fermi Paradox. Then there's von Neumann probes, named after mathematician John von Neumann. These tiny, self-replicating machines would spread exponentially across the galaxy, using raw materials from asteroids or moons to build copies of themselves. A single probe could theoretically blanket the Milky Way in 1,000,000 years, a blink in cosmic time. Some theories suggest the reason we haven't found alien probes is because we haven't recognized them. Ancient artifacts on Mars, oddly metallic asteroids, they might not be natural at all, but dormant machines waiting for a trigger. And if humanity ever launches its own, we'd effectively become the architects of the same mystery that haunts us today. Interstellar communication adds another layer. Projects like SETI messaging to extraterrestrial intelligence deliberately beam signals at nearby stars, while Breakthrough Listen scans millions of frequencies for replies. But here's the catch: our earliest radio broadcasts have only traveled 100 light-years. In a galaxy 100,000 light-years wide, we've barely whispered. Future technologies like laser arrays or quantum entanglement could change that, allowing real-time conversations across the void. But with every signal sent, we're not just searching for aliens. We're announcing ourselves, joining a cosmic conversation that might have been waiting for voices like ours all along. The unsettling truth is this: the Fermi Paradox might not be about absence but timing. Every civilization could face the same choice: expand, communicate, and risk becoming the aliens others fear, or stay silent and vanish without a trace. We're standing at that crossroads now. The technologies we develop, the signals we send, even the way we handle our own survival, all of it could determine whether humanity becomes a footnote in the universe's story or the answer to its greatest mystery. The silence isn't just something to solve, it's a challenge to fill. For decades, humanity has been straining to catch even the faintest whisper from the cosmos, proof that we're not alone in the universe. The search for extraterrestrial intelligence, or SETI, has been our collective ear pressed against the galactic door, listening for signals that never come. Modern efforts like Breakthrough Listen have taken this search to staggering new heights, employing some of the world's most powerful telescopes to scan millions of stars across vast swaths of the electromagnetic spectrum. Yet the silence persists, broken only by tantalizing but fleeting anomalies like the infamous WOW signal, a burst of radio waves in 1977, so strong that the astronomer who discovered it scribbled "Wow" in the margins of the data printout. It matched the expected signature of an artificial transmission, appearing just once and then vanishing forever, leaving us to wonder, was it a cosmic hello or just celestial static playing a cruel joke? Radio telescopes have long been the workhorses of this search, sweeping the skies for narrowband signals, deliberate broadcasts distinct from the broadband noise of natural cosmic phenomena. The logic is simple. Any civilization advanced enough to communicate would likely use focused radio or laser pulses, the interstellar equivalent of shouting across a crowded room. But the scale of the challenge is staggering. Imagine trying to hear a single conversation in every language ever spoken, happening simultaneously across every city on Earth while standing on the Moon. That's the noise floor SETI combats, a universe buzzing with pulsars, quasars, and the faint afterglow of the Big Bang, all drowning out potential whispers of alien intent. Breakthrough Listen, launched in 2016, represents the most ambitious effort yet, dedicating thousands of hours on facilities like the Green Bank Telescope and the Parkes Observatory to monitor the million closest stars. It's not just radio waves under scrutiny, optical lasers are also in the crosshairs. A sufficiently powerful laser could outshine its host star for nanoseconds at a time, a deliberate, unmistakable beacon. But even with this cutting-edge tech, the needle in a haystack problem remains. The Milky Way alone contains up to 400 billion stars. Scanning them all would take millennia, and that's assuming aliens are broadcasting in frequencies or patterns we can recognize. The WOW signal's enduring mystery underscores how maddeningly elusive this search can be. Detected at Ohio State University's Big Ear telescope, it lasted 72 seconds, the exact duration the telescope could fix on a single point in the sky, and matched the frequency of hydrogen, the universe's most abundant element and a logical choice for an interstellar greeting card. Yet follow-up scans found nothing, no repetition, no modulation, no accompanying data, just silence. Some argue it was a passing comet's hydrogen cloud reflecting sunlight, but the debate rages on. The signal's tantalizing ambiguity is a microcosm of SETI grand frustration. The more we look, the more the universe seems to dangle possibilities just beyond our grasp. But what if we're searching wrong? The assumption that aliens would use radio or lasers might be as quaint as expecting a smartphone in the Middle Ages. Advanced civilizations could communicate via neutrino beams, quantum entanglement, or something beyond our current physics. Even our own planet is growing quieter as fiber optics replace radio towers, a trend that might be universal. The golden age of accidental broadcasts, like our early TV signals leaking into space, could be vanishingly brief in a civilization's lifespan. We might be listening for ghosts of a technological stage most species quickly outgrow. The silence isn't just a technical challenge, it's a mirror. Every null result forces us to confront how little we know, not just about aliens, but about the nature of intelligence itself. Are we pioneers, latecomers, or outliers? SETI's real gift might not be contact, but humility. The universe owes us nothing, and yet we keep listening. Sending deliberate messages into the cosmos isn't just a scientific endeavor, it's a gamble with stakes we can't fully calculate. Known as METI, Messaging Extraterrestrial Intelligence, this practice flips the traditional SETI approach on its head. Instead of passively listening, we're actively shouting into the void, beaming tightly focused signals at nearby stars in the hope that someone or something might shout back. But here's the catch: what if the wrong ears hear us? The debate over METI splits the scientific community down the middle, pitting boundless optimism against sobering caution, with humanity's future potentially hanging in the balance. Supporters of METI argue that playing it safe gets us nowhere. The universe won't hand us answers if we don't ask questions. Astronomers like the late Alexander Zaitsev, who famously broadcast the teen-age message from Ukraine's Evpatoria radar in 2001, saw METI as the next logical step. After decades of silence, maybe we just need to speak up. After all, our accidental radio and TV signals have already leaked into space for over a century, announcing our presence whether we like it or not. Deliberate messages, they argue, are crafted clear, concise, and packed with mathematical and scientific concepts any advanced species would recognize. These aren't cosmic spam. They're carefully composed letters sealed in interstellar bottles, floating toward stars with promising exoplanets. But critics fire back with a chilling counterpoint: we have no idea who's out there. The dark forest theory looms large here, the idea that advanced civilizations might see newcomers as threats, competitors for scarce cosmic resources. By announcing ourselves, we could be painting a target on Earth. Stephen Hawking famously warned against this, comparing METI to the indigenous peoples of the Americas signaling Christopher Columbus. The outcome, he argued, might not be contact but conquest. Even if aliens aren't hostile, their mere existence could destabilize human society. Religions, economies, even our sense of identity might shatter under the weight of knowing we're not alone. Then there's the timing problem. METI assumes other civilizations want to talk. But what if they're like us, transitioning from radio to fiber optics, their broadcasts growing fainter by the decade? Or worse, what if they've moved beyond physical communication entirely, relying on quantum networks or some unfathomable dark matter medium? Our carefully crafted messages could arrive at a civilization that abandoned radio millennia ago, their receivers long since repurposed or rusted away. Yet the greatest risk might not be who hears us but who doesn't. The distances involved mean any response could take centuries if it comes at all. By then, humanity might be unrecognizable, scattered across the stars or collapsed into ruin. METI isn't just a message, it's a time capsule, a flare shot into the dark by a species that can't even guarantee it'll be around to see if it's answered. But here's the twist: inaction might be just as risky. If every civilization stays silent, the universe remains forever fragmented, intelligence isolated by fear. METI at its core is an act of cosmic courage, a bet that the universe is more welcoming than we fear, and that the rewards of connection outweigh the perils. The real question isn't whether we should send messages, it's whether we're brave enough to live with the consequences, whatever they may be. Picture a civilization advanced enough to dream of the stars but bound by the same cruel laws of physics we are. No warp drives, no wormholes, just the slow, grinding reality of interstellar distances. Their solution, not sleek starships zipping between galaxies, but vast, lumbering arcs floating cities adrift in the void, carrying generations of explorers who'll live and die before their descendants reach another world. These wouldn't be voyages measured in years, but millennia. A single journey could outlast entire human civilizations. And if this is how intelligence spreads across the cosmos, the Fermi Paradox might have a simple answer: they haven't arrived yet. Consider the numbers. Even at 1/10 the speed of light, a blistering pace for conventional rockets, a trip to the nearest star would take 40 years. Reach farther and the timelines stretch into absurdity. A voyage to a potentially habitable planet like TRAPPIST-1, 39 light-years away, would demand 4 centuries of travel. That's longer than the United States has existed as a nation. Now imagine a ship holding thousands of passengers, their great-great-grandchildren, the ones who will finally step onto alien soil. This isn't just engineering, it's sociology, a test of whether a society can stay cohesive across generations locked in a metal hull. But here's the twist: such ships might be invisible to us. A generation arc wouldn't blaze across the sky like a sci-fi starship. It'd be a dim, cold relic, its engines silent after the initial acceleration, coasting on momentum alone. Our telescopes scan for radio signals or Dyson spheres, flashy, high-energy tech but a dormant arc. It could drift right through our solar system, camouflaged as just another icy asteroid in the Kuiper belt. Even their communication might be minimal, tight beam lasers aimed solely at their destination, not wasteful broadcasts into the void. Then there's hibernation. If biology permits, crews might sleep through the centuries, their bodies slowed to near death by cryogenics or torpor tech. Imagine a fleet of frozen explorers, their ships on autopilot, waking in shifts to check systems before returning to slumber. To outside observers, these vessels would look like tombs, silent, dark, devoid of the energetic signatures we associate with life. A hibernating arc might park in orbit around a star, waiting for some internal clock to tick down, while civilizations like ours rise and fall beneath its radar. The unsettling possibility: we could be surrounded by these travelers and never know. A dormant arc might lurk in our Oort cloud right now, its occupants unaware or indifferent that Earth hosts a noisy young species ripe for contact. Or worse, previous arcs might have passed through our neighborhood millions of years ago, finding nothing but dinosaurs or primordial slime before moving on. The universe's silence wouldn't mean absence, just terrible timing, and that's the humbling truth behind generation ships. They don't just solve the speed problem, they redefine what patience means on a cosmic scale. While we fret over decades-long radio silences, other civilizations could be playing a game measured in epochs, their ambitions stretching beyond mere stars to the unfathomable future. The Fermi Paradox might not be a mystery at all. It might just be a waiting room, and we're the ones who got here early. Quantum mechanics might be the ultimate cosmic magician's trick, hiding civilizations in plain sight through the sheer weirdness of reality itself. Imagine a universe where alien societies don't just exist beyond our telescopes, but operate on levels of physics we're only beginning to grasp. What if their very nature defies our classical understanding of space and time, making them as invisible to us as radio waves are to the naked eye? Start with entanglement, quantum physics' most baffling phenomenon. Particles linked across vast distances, where changing one instantly affects its partner, no matter how far apart they are. To a civilization mastering this, communication wouldn't rely on sluggish radio waves plodding at light speed. Instead, they'd trade messages instantaneously, bypassing the delays that render interstellar conversations impractical. Picture a galactic internet humming beneath the visible universe, its data encoded in entangled particles, utterly undetectable to our crude antennas. We'd never hear their whispers because we're stuck listening for the wrong language. Then there's the multiverse theory. If parallel universes exist, each a slight variation of our own, an advanced species might have cracked interdimensional travel. Their cities could sprawl across realities, their presence flickering in and out of our cosmic neighborhood like shadows under a strobe light. UFO sightings. Maybe not spacecraft, but glitches, moments when their dimension briefly overlaps with ours. The idea sounds like science fiction, but consider this. Quantum mechanics already suggests particles pop in and out of existence. Why not entire civilizations? Even more unsettling is the possibility we're living in their simulation. If quantum behavior is fundamentally probabilistic, governed by probabilities until observed, it's eerily reminiscent of a computer program rendering details only when needed. Advanced beings might have engineered this universe as an experiment, tweaking quantum states like code. Their observations could be the reason particles behave so strangely when we measure them. In this scenario, the Fermi Paradox isn't about missing aliens, it's about being unable to see the players outside the game. But the wildest theory, quantum cloaking. Schrödinger's cat famously exists in a superposition, both alive and dead until observed. Apply that to a planet. What if entire worlds exist in quantum states, neither here nor there until someone looks? A civilization could have engineered this deliberately, shifting their home into a superposition to evade detection. They'd effectively exist everywhere and nowhere, visible only when they choose to collapse the wave function. Here's the kicker, we might already have evidence. Quantum anomalies in lab experiments, unexpected particle behaviors, statistical flukes, could be traces of these hidden interactions. Some physicists argue that dark matter's gravitational effects hint at entire sectors of reality operating beyond our perception. If that's true, the cosmos isn't empty. It's layered like an onion, with civilizations folded into dimensions or quantum states we can't yet peel open. So the silence isn't silence at all. It's a curtain, and behind it, the universe might be teeming with life, just not in any form we've learned to recognize. The Fermi Paradox doesn't need a cosmic graveyard to make sense. It might just need a better pair of quantum eyes. Hollywood has always been obsessed with the silence of the cosmos, turning the Fermi Paradox into a playground for imagination. Take Contact, the 1997 film based on Carl Sagan's novel, where humanity's first encounter with aliens isn't a fleet of warships but a cryptic radio transmission, a deliberate echo of our own search for extraterrestrial intelligence. The movie mirrors real-world SETI efforts, but with a twist. The message contains blueprints for a mysterious machine, suggesting advanced civilizations might send knowledge rather than greetings. It's a hopeful vision, one where aliens act as cosmic mentors, but it also hints at a darker truth that the universe might be full of civilizations too far ahead to bother with casual chit-chat. Compare that to Arrival, where linguistics becomes the key to unlocking alien intent. The film's heptapods don't just defy expectations with their inkblot language, they shatter the assumption that all intelligent life would think like us. Their perception of time as nonlinear forces humanity to confront the limits of its own cognition, a brilliant metaphor for how the Fermi Paradox might not be about absence, but about a failure of translation. Science fiction often leans into the paradox's darker implications. The three-body problem, Liu Cixin's groundbreaking novel, presents a universe where civilizations hide in fear, terrified of attracting the attention of predatory aliens, a chilling embodiment of the dark forest theory. Here, the paradox isn't just unanswered, it's a survival strategy. Broadcast your location and you're marked for annihilation. The book's infamous Dark Forest Strike, where a distant civilization obliterates another preemptively, turns the cosmos into a nightmare of paranoid silence. It's a far cry from the optimistic first contact of Star Trek, where the galaxy buzzes with diplomacy. Instead, Liu paints a universe where trust is suicide, and the only safe move is to stay quiet or shoot first. Then there's 2001, a space odyssey where the monoliths represent an intelligence so advanced it operates on geological timescales. The film's aliens don't chat or conquer, they nudge. Their presence is subtle, their motives inscrutable, and their interventions millennia apart. Kubrick's vision aligns with the Sentinel hypothesis, the idea that advanced civilizations might observe without interfering, waiting for us to reach a threshold of maturity. The monoliths aren't just artifacts, they're cosmic SETIs, testing humanity's readiness for the next evolutionary step. It's a stark contrast to Independence Day, where the paradox is solved by hostile aliens who finally show up, not to talk but to strip mine the planet. The film's explosive answer to "Where is everybody?" is simple: they're coming and they're hungry. Even comedies tackle the paradox. The Hitchhiker's Guide to the Galaxy famously mocks humanity's obsession with the question by revealing Earth was just a supercomputer built to find the ultimate answer, a joke that underscores how absurd our assumptions might seem to a galaxy teeming with life we're too primitive to notice. Douglas Adams' absurdist take highlights a sobering truth. The universe doesn't owe us answers, and the silence might not be a puzzle to solve, but a punchline we're not in on. What makes these stories so compelling is how they refract real scientific debates through the lens of drama. Contact's patient, signal-based first contact mirrors the optimism of SETI, while the three-body problem's paranoid cosmos echoes the grim warnings of those who oppose METI. Arrival challenges the anthropocentric bias that aliens would think or communicate like us, a critique real astrobiologists grapple with daily. And 2001 suggests that the paradox might not be about technology, but about evolution itself. Fiction doesn't just entertain, it lets us stress test theories, playing out scenarios too complex or terrifying for textbooks. Yet for all their creativity, these stories share a common thread. The Fermi Paradox isn't just about aliens. It's about us. Whether the answer is hope, fear, or cosmic indifference, pop culture reminds us that the silence of the stars is a mirror. What we see in it says less about the universe and more about what we're afraid or desperate to find. After exploring the staggering possibilities behind the Fermi Paradox, from the Great Filter's grim warnings to the cosmic hide and seek of the dark forest theory, one thing becomes clear: the silence of the universe isn't just a mystery. It's a mirror reflecting our deepest hopes, fears, and unanswered questions about our place in the cosmos. Perhaps we're alone, a statistical fluke in an otherwise sterile expanse. Or maybe the universe is teeming with life, but hidden in dimensions, quantum states, or civilizations so advanced they've transcended the need for starships or radio waves. The rare Earth hypothesis suggests we might be the universe's first draft, while the simulation argument implies we're lines of code in an alien supercomputer. Each theory offers a radically different vision of reality, yet all share one haunting thread. The answer could redefine not just science, but what it means to be human. So where does that leave us? The paradox isn't just a puzzle to solve, it's an invitation. An invitation to keep searching, to stay curious, and to confront the uncomfortable possibility that the truth might be stranger than anything we've imagined. Every telescope scan, every signal analyzed, every exoplanet studied brings us closer to understanding whether we're pioneers, outliers, or simply late to the party. And that's the beauty of it. The search itself is what pushes us forward, compelling us to innovate, collaborate, and dream bigger. Now it's your turn. What do you think lies behind the cosmic silence? Are we alone, or is the universe hiding wonders beyond our current comprehension? Drop your boldest theories in the comments. Let's turn this existential question into a conversation. And if you're as captivated by the mystery as we are, hit subscribe to join us on the next mind-bending exploration. The universe is vast, the questions are endless, and the journey to uncover them, well, that's just getting started.